Hi, so let's do this lecture online. Now I'll do all of section 2.4, even though we've covered a little bit of it already, but just to make it a little bit self-contained. So analytic functions. So analytic functions are functions that are at each point equal to a convergent power series, right? So given an open set U, we have a function. Well, a function is analytic. It's a function on U. If at every P, every point P in that U, there exists a disk of positive radius centered at that point, and a power series that converges to F on that disk. Now, this you could have some different disk, of course, at every point. This R could be small, doesn't have to be very big, at least not for the definition. And you just have to have it at every point. And at every point you have to have a power series, and the power series must converge to F. So it can't just be like, if you remember, Taylor series. So a Taylor series, we'll see that this one will be actually a Taylor series, but we just don't want it to be just a Taylor series. We need it to actually converge to the function in the entire disk. All right. So eventually we'll see that holomorphic functions and analytic functions are one and the same. It is the same class of functions. Now that's actually not as easy to prove. Now today we'll prove that analytic functions are holomorphic. Now, to show that holomorphic functions are analytic, they'll require a lot more machinery. So this is the easier direction. Is analytic implies holomorphic. Basically, analytic implies complex differentiable. Now, a subtle point is that it is not immediate that a power series is itself an analytic function, right? We'll show that power series is holomorphic, but we don't quite immediately know that a power series that you can expand it around other points, not just that point where it's defined, but around every other point where it converges. And actually, to prove that, what's going to be interesting is that we'll use the fact that power series are holomorphic, and then the whole shebang, the whole thing, going back to analytic. So once we know that holomorphic functions are analytic, we'll see that power series are going to be analytic. All right. So that's coming. That's not today. All right. So this is the proposition about differentiating power series. So if we have a power series defined in some disk, so really we mean it converges in this disk, then F is complex differentiable at every z. So in particular, it's holomorphic, right? So it's holomorphic in the disk, and the derivative is given by this power series, which is precisely what you'd get if you just did it term by term, right? If you just do it, as they say, formally, right? And the derivative power series converges in the same disk, right? So you can just basically differentiate power series term by term. So let's prove this. So without loss of generality, let's just assume that P is 0, just so that we don't have this P there, right? To make things simpler. And let's try to differentiate this this single term over there, right? So really, we just need to differentiate z to the n. Remember, we made p to be 0, right? And we're doing it at some z naught, some point z naught. So to differentiate, of course, you first write down the difference quotient, right? You need to figure out what happens, right? So you write down the difference quotient for z to the n at z naught. That's just this expression. And then it's the same idea as the geometric series, geometric polynomial, right? It's the summing. When we had 1 plus z squared and so on, right? So if you, instead of 1, if you put in z naught to the n, and then z naught to the n plus z naught to the n minus 1 times z plus, and so on, you can get this formula over here, right? This formula over here. All right. Now, the point here is that this is clear. This clearly converges to the right thing as z goes to z naught. We have that the difference quotient goes to what you'd expect the derivative to be, right? At least for z to the n. So at least for each term, right? So let's do it for the entire series, right? Let's look at the difference quotient for the entire for the function for f, right? So when we can add and subtract power series. So that was the exercise I was talking about before. That's actually rather easy. So we can just add the series, right? And you can add them term by term. So we get this guy over here. Now, this thing looks like the difference quotient that we just computed. So we can substitute that. Now, if we could take the limit as z goes to z naught over here, right? That means taking it outside of this guy, right? Outside of this whole thing, right? But we know how to take it out here, in here, right? Inside, right? We don't know how to take it inside this limit, right? This infinity means that there is a limit, right? So what we need to do is to show that the limit goes in, right? One way to do that is, these guys, or really the partial sums of these, right? Those are continuous functions. Those are just polynomials, right? Because the z minus z naught, they just divide it out, right? So the partial sums are polynomials. They're continuous, right? So if we can show that the partial sums converge uniformly in some neighborhood of z naught, so uniformly in z, then, uniform limit of continuous functions is continuous, right? So that means that the whole thing would be a continuous function of z, right, in a neighborhood of z naught, and we could just take the limit as z goes to z naught, right? So, all right. So, right. So that's that's what I just said, right? All right. So we're gonna use, as we've seen this before already, right? So p is just 0 in our case, right? We're gonna set up these three. We have the R disk, right? But we're gonna set up these two new guys, S and R, right? And they're just gonna be two smaller numbers, less than R, and we're gonna assume that Z and Z naught are in the smaller S disk, right? All right. So let's look at. Assuming actually we're going to show that it converges uniformly, absolutely. So let's look at the absolute absolute values here, right? And just let's look at these terms of the series, right? And we just apply triangle inequality to put the absolute values inside, and then we're gonna apply the right. I mean, we have z is less than s, and the same thing with z naught, right? Right. So that's why we get this inequality, right? And now once we do that, then this is just n times this thing, right? So that's why we're getting this. And now we make this a little bit more complicated by basically multiplying by r to the n minus 1 over r to the n minus 1, so that we get this expression over here. Now, why do we do that? Well, we do that because this guy is bounded, right? The sequence of these guys is bounded, right? Well, I mean, you really know that the sequence without the minus 1, that guy is bounded. But that's clearly implies that the sequence with the minus 1, because it's just you divide by r, right? So that's a bounded sequence because f converges in this disk, and r is less than capital R, right? Right. So that's why we get this thing, right? So f was a convergent power series, and that was the proposition that we saw before, right? So there is some bound, there is some m, right? So let's look at the nth root of this guy, right? Which is the nth root of this guy, right? So that's what we're doing here. And let's just mess around with this. So this we know is bounded by m, right? So that's why we're getting the m over here. And so now we have this expression out here. Now, square root of n, the nth, not square root, sorry, the nth root of n, that goes to 1. The nth root of m, right? M is not moving. That also goes to 1. And then s over r to the n minus 1, the nth root of that just goes to s over r, right? So really, this whole thing, as n goes to infinity, goes to s over r. And the point was that we picked s to be less than r, so that we get that the limit of this is less than 1, or really the lim sup of this. We don't know if the limit exists, but the limit of this thing exists, right? But the lim sup of this is definitely strictly less than 1, right? All right. So that means that this series converges by the root test. Oops. And that means that this guy over here, this guy over here, right? That converges uniformly in Z on this S disk, right? All right. So, right, because this this thing over here, right, that converges, and there is no Z in there, right? It was for all Z that are in this S disk, right? Right. So that means we can swap the limits, right? We can take the limit, right? Because the limit of this now exists, right? Because it's it's the limit inside, right? Because inside we can clearly take the limit. This is just a polynomial, right? And we know what the limit inside is. It's precisely the derivative, right? So, all right. So we could differentiate now. S and R were arbitrary, right? Arbitrary less than capital R. I mean, we'd get a different capital M in the proof, but we get the same, it's the same result, right? So this will work for any z0. If I need to z0 close to the boundary, I just choose a larger S and R, right? And clearly the convergence is going to go at different rates, but it always works, right? Just by choosing sufficiently large S and R, but still less than capital R. All right, now it's useful to look at this result and look at what it means when you basically do an induction, right? So just keep repeating it. So suppose it starts basically the same way, right? You have this convergent power series on some disk, right? Well, notice that the derivative, right, was again a power series, right? You can reindex this if you want, right, to make it look like a power series, right? Make it start from n equals 0, right? So that's a power series. So a power series, it again converges, right? So you can keep going, right? And you only need to figure out, well, what is you can just keep differentiating formally, right? So you just are differentiating the each term separately, right? And you can do that, right? This is the formula, right? And again, the kth derivative is converges in the same disk, and you can do this as many times as you want, right? So it's infinitely differential, right? So that's just applying that theorem k times. Now, a neat thing about this is this formula over here, right? That if I plug into the kth derivative, right? If I plug in p, right, that will kill everything but ck, right? So I will actually get so everything but the term where I'm getting that n minus k is 0, right? Everything else, every other term in this series is 0, right? So I get a formula for the coefficients in terms of the derivative, right? So the consequence of that, let me just make sure that I'm not hiding anything behind my face. So the consequence of that is that the power series is unique, right? Because we have because the coefficients are unique, right? And we have a formula for the coefficients. Once you know f, once you know the function, right? Once you know what it converges to, you know what the series is. So two different series cannot converge to the same function because I get the coefficients in terms of the function, right? So they're given. I can't choose different coefficients. Different coefficients will go to a different function, right? Because it will have different derivatives, right? So that's a neat result from that, from being able to differentiate, right? Is that we can actually compute compute the coefficients from the values of the function. And another interesting thing is that the coefficients only depend on the values of f in an arbitrarily small neighborhood of the point P, right? Because to compute a derivative, you only need an arbitrarily small neighborhood. You need some neighborhood, right? You need some open set, but it doesn't have to be very large, right? The power series could converge in a really big disk, but to compute the derivative at the point, I just need a small small neighborhood, a small disk maybe, right? It can be really, really, really tiny, right? And it still gives me the same constants, right? The same coefficients, right? And I don't need to know what the values of the functions are out here, right? Outside of that small neighborhood. All right, so now we can apply this to analytic functions, right? So if we have an analytic function, right, it has a power series at every point. Now, if it has a power series at every point, then that that power series, and therefore the analytic function, is holomorphic, right? Furthermore, the derivative is a power series. Now I can do this at every point, and therefore the derivative is analytic, right? So an analytic function is infinitely complex differentiable, and the derivative is analytic. Again, we don't yet know that a power series is analytic, right? So this is, in some sense, a sort of a weaker statement, right? But it's going to be the same because power series are analytic. We just haven't proved it yet. All right. Now, let's use this stuff to define the exponential. So before, we defined the exponential using Euler's formula, right? Well, we just defined it in terms of the real exponential and sine and cosine. And it's maybe not quite so satisfactory, right? I mean, we are, this is a complex analysis class. We should define everything in a complex analysis way in some sense, right? We show that this is holomorphic, right? So this function e to the z is a holomorphic function. So let's define this in a different way. In a more sort of differential equations kind of way, right? So if you remember how in differential equations, when you studied power series methods, how you would solve things. So that's what we're going to do, right? So we want to show that this series, this power series, is the unique convergent power series at the origin that satisfies this equation f prime, its own derivative, it equals its own derivative, and f of 0 is 1, right? So we're solving this initial value problem, differential equation, right? And moreover, the series converges in C, which is easy. And it equals e to the z, which we have defined in this way, right? So we already have e to the z defined. So we're not really using this to define. We could have used this to define e, the exponential, but we're going to show that it's actually equal to our previous, previous definition, right? Really, previously, the point is that this exponential satisfies these two things as well. And we're going to show that that will mean that it is actually the same thing. All right. So let f be a convergent power series, right? So just suppose that we have a convergent power series, right? And let's first look at this guy. That's the easy one. If we plug in 0, we get precisely C naught, right? And we want it to be 1, so we know that C naught is equal to 1, right? So we know C naught. So we're somewhere. We've started, we have one coefficient is given, right? So now let's figure out the rest. Now, we know that f prime is supposed to be equal to f, right? All right, so let's compute f prime. Right, so f prime, well, we know that we can differentiate term by term, right? And we reindex so that the power is n, right? So it's just writing the same thing, right? Now, this series is supposed to be equal to f, right? Which is supposed to be this this series over here, right? So that means that these two terms are supposed to be equal, right? Because coefficients of power series are unique. So I cannot have, if two power series are equal, right? The two power series at a single point, so in this case, the origin, if they're equal, the coefficients are equal, right? So that means that we have this equation. Well, that gives us all the CNs, right? Because we know C naught from C0 we get C1, from C1 we get C2, and so on. By induction, you can easily show it's always multiplies by by n, right, or n plus 1 if you go, right? So it's or divides really. So we have that Cn is 1 over n factorial as we want it, right? So that's the that's the function, right? That's the power series, right? It is the unique power series, right? We've used this and the initial condition, and we got that Cn must equal this, right? Now, it converges. That's fairly easy. You just do root test, ratio test, something like that. All right. Now, let's show that it equals the exponential. So we've shown that the exponential is holomorphic and equals its own derivative, right? So that's what we know, right? And here, and it's 0 and it's 1 at 0. So let's use that, right? And let's look at the ratio. Let's look at f over the exponential, right? I'm writing x just to make it, because I want to use x prime, right? It would be a little hard to write with e to the z, right? So that's why I'm writing x here, right? And let's differentiate the quotient, right? So quotient rule, right? So you have that. Both are holomorphic. This makes perfect sense, and we know that exponential is never 0, right? So this makes perfect sense, right? So it makes perfect sense. Now, in the top, right? So I have this expression. Well, f prime is f, right? So f prime is f. Exponential prime is the exponential. Well, that means that this just the numerator here is 0, right? So this is 0, right? Well, what does that mean? That means that f over the exponential is a constant, right? I mean, we've proved that if the derivative of something is 0, it's constant, right? So we have that this is constant. So f is c times the exponential for some constant c. Let's figure out what that constant is. Well, f at 0 is 1, exponential at 0 is 1. That constant had better be 1, right? Well, that's it. That's it. That's the proof, right? That's everything. All right. So the final term in this, since we're on a roll, identity, right? So, we're missing 2 days for snow, right? So let's, let's prove it out. And this is, also a nice simple one. All right. So identity. Suppose we have a domain, and the domain, that's important. So it's a connected open set, right? And we have an analytic function on U, on this domain. And we look at the 0 set. So here, another way that you can write this, it's the inverse image of 0. It's the set of points where f is 0, right? Now, if this set has a limit point in U, then f is identically 0. So if the zeros kind of go and they sort of converge to some point, then the function must be 0 identically everywhere, right? In all of U, right? That's what we're using, connectedness. Now, in other words, what does it mean? It means that the zeros are isolated. If f is 0 somewhere, it's not 0 in some neighborhood of that point, right? Unless, of course, it's identically 0. If it's identically 0, then 0 everywhere, right? All right. So as I said, these are called zeros. that's a sometimes it leads to some confusing confusing statements, right? Saying like if f of 0 is 0, we'll say that f has 0 at 0, right? Has a 0 at 0. It sounds weird, but yeah, that's just what it is, right? So instead of roots, we use zeros often in complex analysis. It's the same thing. It's the root of a function. All right, the common application of this theorem is that if you have a holomorphic function and it's 0 on some small non-empty open set, right? And that's definitely, you have limit points, right? That's a weaker statement over here. But that's a lot of times where this comes in. If a function is 0 on a non-empty open set, then it's identically 0. Right? That's actually, it's very easy to prove from that if you have two holomorphic functions and they're equal on some open set or on some set that has a limit point, then they're actually the same function. Then they're equal, right? You could instead of identically equals to 0, you could use a g, right? That's not hard to show. All right, so let's prove this, right? So suppose f is not identically 0. If it's identically 0, we're done, right? So let's suppose it's not, right? And we're going to show that all the zeros are isolated. So the set of zeros is closed because it's f inverse of 0. F is continuous, right? So the zero set of a continuous function is always closed. And we need to show that it's not just closed, it's isolated points, right? So without loss of generality, let's look at 0. Can do it at any p, but let's just do it at 0. Let's suppose that 0 is is a 0. So 0 is a 0 of f, just as I said. It sounds weird, but that's what it is. And let's suppose that it's not in the interior of the 0 set, right? If it's in the interior, we'll handle that separately, right? So let's suppose it is a 0 and it's not in the interior of the set of zeros, right? So we write down the function as a power series, right? It's an analytic function, right? So it's if it's 0 at 0, right? Because 0 was in the 0 set. Therefore, C naught is 0, right? All right. So let k be the smallest number, smallest integer, such that this Cn is non-zero, right? Now, there has to be such a number. If all the Cn's are 0, then f is just identically 0, right? Because you just had the 0 series, right? So there has to be at least one that is non-zero. It's not, so k is not 0. It's a positive integer, right? And there has to be a smallest one that's non-zero because it's not identically 0, right? Now, what that means is that we really are starting this power series at k, really, right? And if we're starting this power series at k, we could, all the terms have z to the, I can divide z to the k out of them, right? So I can write this power series over here. I can write it like this, right? And this power series, that's this g, right? So let's just call it g, right? So g is a convergent power series, and I have that f is z to the k times g, right? Now, ck was not equal to 0. Therefore, g at 0, which is equal to c to the k, right? If you look at this, right? If I plug in 0, right? The only term that's non-zero is when n is equal to k. So it's just c to the k, and we know that that's not 0 by assumption, right? So we actually have that f is z to the k times something that's not 0, right? Now, a convergent power series is differentiable, therefore it's continuous, right? Well, if you have a continuous function and it's non-zero somewhere, it's non-zero in a whole neighborhood, right? So G is not zero in a whole neighborhood of zero, right? There's some, if we have the origin here, there's some neighborhood where G is not equal to zero, right? So what does that mean? Well, that means that the only way that f could be zero in a neighborhood of the origin is for z to the k to be zero, right? Because g is not zero at all, right? So, but z to the k is only zero at zero, right? So that means that zero is an isolated zero of f, right? All right. So we're basically done. Points of ZF are either interior points or isolated points, right? Either you're in the interior or you're isolated, right? Now, suppose let me give it a name. Let me say Z prime sub F are the interior points. B, not bet, B the interior points, right? We're not betting anything. So let Z prime be the interior points, right? So the non-isolated points of ZF, right? Now, this Z prime is closed. It's maybe a little bit harder to see, but ZF is closed, right? Now, if I have a point in ZF that's not in ZF prime, I cannot approach it by points in ZF prime, right? Because ZF prime is in the interior, right? I cannot approach an isolated point, right? Well, I mean, it's basically the set of non-isolated points. This set must be closed, right? That's that's what this means, right? You cannot approach non-isolated. You cannot approach isolated points in a set, right? So therefore, ZF prime must be closed, right? Well, ZF prime is closed. It's also open, right? I mean, it's the interior of ZF, right? So it's open, it's closed. So therefore, because U is a domain, it's closed. It's connected. Either U is ZF prime or it's an empty set, right? So, and we know that it's not all of U because we said that F is not identically zero, right? So therefore, ZF prime is the empty set. That means that ZF are just isolated points, right? And we're done, right? So that's the lecture. So hopefully by Monday the snow will be gone. All right. So see you Monday. Oops.